You were entrusted with a vault full of mysterious treasure, but it can only be reached after decoding this number, an RSA-250 code. Banks use similar codes which are around 670 digits long or 2048 bits.
These asymmetric key encryptions use a trapdoor function that's easy in one direction but not that straightforward in reverse. When I'm sending a secret message, I would use their long public key number to garble my message into a ciphertext, which would be impossible to ungarble without knowing the two prime factors that made that number.
This is where quantum algorithms come in.
Using the quantum states of tiny subatomic particles and their effects in quantum systems like locality, entanglement, superposition, and interference, we can get to the solution much faster in less steps. Even the general number failsafe takes much longer than Shor's quantum algorithm, which could solve complex problems in polynomial time, like a super powerful laser that could cut through any encryption. Quantum devices consist of qubits, which unlike normal bits are in a combination or superposition of 0 and 1. If you have 300 qubits, you can represent more states than there are particles in the observable universe. But since you can only measure a single random value from the superposition of states, you need a smart way to get the one state that you want. For instance, in Shor's algorithm, let's say a number n is the product of two primes a and b. You make a random guess g at a number that might share factors with n, but g ends up not sharing factors with n. Due to the awesome property of coprimes, you can multiply g by itself q times to eventually get a number m times n plus 1, forming a periodic cyclic function that repeatedly runs through a set of values for a period q. So our factor finding problem becomes a period finding problem, which can be reduced to a billion hidden subgroup problem and solved quickly on a quantum device using number theory and quantum Fourier transform. The QFT repeats with a frequency of 1 by q to cause all possible wrong frequencies to destructively interfere, leaving a single quantum state, 1 by q. We invert this to get the period q, and using Euclid's algorithm, we find guess g raised to half of period q plus or minus 1, which are much better guesses for factors a and b, break the code, and finally get to that treasure. The spooky physics of subatomic particles can be exploited to
Invent medicines, develop trading strategies, and create secure methods of communication in the foreseeable future.